Last video ended right here. Now that was the z basis. Let's look at the x basis. Now I'm going to make a definition for the x basis, but I'm going to refer to this fact of the measurement. When the electron was prepared on the z basis, in other words, you measured it on the z basis and it was passed over to a measurement system on the x-axis, you got a 50% probability. Now what's this 1 over square root of 2? Well, if you square that, you're going to get 1/2. And we went through this in another fashion, but it's the same idea. 1 over square root of 2, and then we're going to have that multiplied times the aligned z or the misaligned z. Aligned or 100% not aligned. Now, we went through this projecting the z on the state, so now we're going to do the x. And what gets more complicated is that we've got these z bra and ket vectors in here that we have to deal with. Okay, notice that when I represent the x, I've got the bra vectors now. This is the version of the bra vector, and this is the cosine theta over 2 from up here, and there's the ket vector for the z plus the e to the I phi sine theta 2 and the ket vector for that. So as we multiply through on this thing, let's see what happens. Well, the z is the brat z is multiplied times the ket z, and that makes a 1. So that leaves us with the cosine theta over 2. The brat z multiplied times the ket minus z, that's going to end up giving us 0 and get rid of this monster right here. Let's see how we can project the probabilities of the x over the state vector here. Now somewhere in here we should be able to see the state vector. There's the state vector plus, so that in these parentheses is the state vector. If I take the bra vector times the ket vector here, that will equal 1, and so that will leave me with cosine theta over 2. If I take the bra vector for the aligned and multiply it times the non-aligned, then that will get rid of this thing. That will just become a 0. Now if I take the bra vector of the not aligned, then that will get rid of one factor of the cosine theta over 2, but it will also put a 1 on this one. But what we're left is with 1 over square root of 2 cosine theta over 2 plus e to the I sine theta over 2. If we want to get the probability, the magnitude of this requires us to use the complex conjugate for one of the factors. And the complex conjugate is shown here with the minus I phi sine theta over 2. And here's the one that's not the complex conjugate. That's what we started with. If I take the 1/2 times all this mess, we start multiplying things out. The e to the minus phi, e to the plus minus phi, that ends up being a 0, so that takes out the sine squared. And what are we left with? if you can follow through, we've got an e to the minus I phi, sine theta over 2, cosine theta over 2, and e to the plus I phi, sine theta 2 over cosine theta 2. So this is as close as we get on this page. 1/2, because the 1 over square root of 2 is squared, and then we have this god-awful mess here. So we have to go to another page to continue on. Carried over from the last page, here's the probability of x, and we've got 1/2, 1 plus cosine theta over 2, sine theta over 2, and then e to the negative I phi plus e to the I phi. Now, let's see what we can do. Over here, I'm going to add these two things together. By definition, e to the negative I phi is cosine phi minus I sine phi, and the other one that is not the complex conjugate, see I've got complex conjugate up there, e to the I phi equals cosine phi plus I sine phi. Now, if we add these two together, the I signs drop out and we get 2 cosine phi. Now, here's something that is going to blow your head open a little bit. 2 cosine theta over 2 sine theta over 2 is equal to sine theta. I say that slowly because this really takes a lot of thinking through it, but with all this stuff here, we can drop down and justify this next line, which is 1 plus 2 cosine theta over 2 sine theta over 2 cosine phi, and then finally we get to 1 plus sine theta cosine phi. Now the important thing is that this phase is part of the probability. So if that phi is something other than 0, then that's going to have a change in the probability. Aren't you having fun with all these brackets and probabilities? This is what we started with on the x-axis. This is what we're going to start with on the y-axis. You notice this plus I and minus I. Now, why would I add that? Well, guess what? We need a difference between x and y. Otherwise, it isn't going to work out. That's a really crude way of saying it, but let's just go with it and live with this idea. Notice the 1 over square root of 2 is still there between the two extremes, the aligned and non-aligned, but we've got this I in front of it to distinguish it from the x-axis. We're putting all this in the z-axis framework because that way we can compare the different axes and the way their measurement bases present the probabilities. I believe we worked through the z projected on the x, and we got 1 over square root of 2. If we take the negative x and the positive x, then if we take their z representations, we can follow through and find out that the z bracket here, aligned bracket, gives us a 1. The non-aligned z bracket gives us a 1. And this gives us a 0, and this gives us a 0. So I've got it all lined up here, and guess what? You project an x on an x, you just get 0, which is, that's logical if I want to stress that this is the non-aligned x and this is the aligned x. Woo! Now, what if based on these definitions, what happens if I take the bra z and multiply it times that? Well, the z multiplied or in it set up in a bracket with positive z, that's just going to give us 1, and this is going to give us 0. So the z projected on the y-axis is just going to give us 1 over square root of 2. I think that's what we expected. Because look, z, y, 1 over square root of 2, z, x, 1 over square root of 2. Now, to prove that why this I is necessary, let me go through and do an x projected onto the y-axis. Everything's expressed in z out here, but we're just working with the x and y bases. So 1 over square root of 2, and then we've got the bra vector here and the bra vector there. Where'd that come from? Well, that came from up here. Up here. It's funny, you can lose your place pretty easy. And then we have the ket vector for the y. Here's the ket vector for the y, plus y. Multiplying these things out, we get a 1 over 2 plus, this just becomes a 1, this becomes a 0, this becomes a 0, and this becomes a 1. So we've got a 1, 0, 0, I. So we end up with a 1/2 1 plus I. Now, what's the magnitude of 1 plus I? Since we've got this imaginary component, I have to take the complex conjugate. Therefore, I've got the 1 minus I and the 1 plus I that we form a result from. So that gives us 1 over 4. And if we multiply this thing out, we're going to get 1 times 1, 1 times negative I, plus I times 1, there's the plus I, and plus I times minus I gives us negative I squared. Well, I squared is negative 1, so that gives us 1 plus 1. It puts 2 in the numerator over 4 equals 1/2. Now, I think that matches stuff up pretty well. To wrap things up, we need to prove that the way we've defined those axes, or those basis vectors, with the z, proves that this is 0. Okay, here we go. If you're still with me, there's 1/2, which is when you square the two 1 over square root of 2 things. Then we multiply these factors together. Z plus z, make that bracket 1. Take z times this bracket, 0. The I non-aligned z times this one gives us 0, and this is the tricky one. I times this one gives us 1, but what's the I value? The I value should be 1. Oh, it gives us plus I squared. Oh, 1 I squared is minus 1. So there's the minus 1.